Okay, the first topic in quant being the correlation and regression. There is some amount which has been covered in L1 also with respect to correlation, but here L2 being more focused towards calculations and application. So we may have to take up some data, do some kind of calculation. So what I am doing is parallelly I am putting up an Excel sheet also to demonstrate how we actually calculate all these things and how do we interpret it. So I'm taking a live data, and based on that we are trying to drive this entire concept. And most of the time, most of our concepts will be driven through that mechanism itself, whether it is FRA or any of the other stuff. So the initial part in this being a scatter plot of the data, where when I want to talk about a correlation or a regression, it's more about the interaction between the two variables. Are they moving together in the same direction? If one is going up, is the other also going up, or is it the opposite direction, or no relation at all? So that is obtained through a simple scatter plot, trying to plot the two data items. Let's say here I am taking a data items right from Jan 05 till Jan 13, the quarterly share price of a company versus the earnings of that company. 1 year, 1 period lag, 1 quarter lag earnings. So I would like to do a scatter plot between these two data items. Now doing a scatter plot is actually in this case is telling me it is giving a relationship between the X value, which is the share price, and the Y value, which is the lag. And in this case what we are observing is it looks like a 45-degree straight line. From the origin it is looking like a 45-degree straight line. A 45-degree straight line will give me an indication that both as X is increasing, probably Y is also increasing. To a large extent we are able to observe that as X values are increasing, the Y values are also increasing. But in some cases, we may observe a pattern that as X is increasing, Y could be falling. Or we could observe a pattern that even if X is increasing, Y may or may not be changing at all. Or in some cases more, some cases less. So based on that, we arrive at what is the relationship between the two variables. So scatter plot is one of the diagrams which help us in finding out the relationship between the two variables. The more it is aligned with a 45-degree straight line, the more I say it is positively correlated, or the more it is a minus 45-degree line, I say it is more strongly negatively correlated. But the more the flatter it is, horizontal it is, I can go with there is no correlation existing, right? And we have found out using a formula also how do I find out correlation. We have used it in our earlier cases, where we said correlation for a sample is nothing but x minus x bar into y minus y bar divided by n minus 1. So here also on this data, let's say if I am trying to find out, n minus 1 is for a sample, and in most of the cases in a real world we work only on samples. So that's where we'll have n minus 1 only for finding out the correlation or covariance, right? So we are going with x bar. So first thing, just as a quick refresher, the x bar is trying to come out with a simple average of the values, average of x, and y bar coming out as average of y. So here I am taking y as the 1 period lag earnings and x as the share price. Okay, so I am taking average of 1 period lag earnings. So this is what it is. Now I want to find out x minus x bar into y minus y bar divided by n minus 1. So going with it, x minus average of x. Then I'm taking y minus average of y. So here every element of x minus the average of x. This is what I do. Alright. So I am doing it for every element of x. I am doing it with respect to the average of x minus average of x. Similarly, I am doing y minus average of y. So I am taking this as y minus average of y. So every element I am subtracting from the mean. That's how we are doing with our. So x minus average of x into y minus average of y divided by n minus 1. So that's where I am looking at the multiplication of those two. X minus average of x multiplied by y minus average of y, and all these things are being summed up. So that's where I am looking at covariance in this case as nothing but the summation of x minus average of x into y minus average of y divided by n minus 1. So here n in our case is 33 observations. Or probably I am starting from the second row. So there are 32 observations. So minus 1 is making it 31. So which is arriving at the covariance being 286,000. Now this covariance, the next question that comes up is it high or low? Covariance as such does not have any boundary. Yeah, it ranges from minus infinity to plus infinity. So there is no base for me to say whether it is high or less. So from that standpoint, only the sign matters. They are positively correlated. They have a positive movement. I can't say how strong is that movement, right? So from that standpoint, a correlation has been introduced, which is simply the normalization part of the covariance, which is nothing but covariance divided by the standard deviations of both of the variables. Now when I am taking the standard deviation of x or as well as the standard deviation of y, just as a process, it is nothing but each x minus x bar, whatever we have done, I can do the squaring, right? X minus x bar, the x minus x bar square, which is coming out to, this is my x minus x bar squared. Same way I do y minus y bar squared. Alright. Now my standard deviation is nothing but x minus x bar squared into x minus x bar squared add up divided by n minus 1. So that is where here I am taking the square root of x minus x bar squared totally added up, which is the summation of x minus x bar squared divided by n minus 1, which is 31 again in our case. So in this case it is saying the standard deviation of x is around 343 units, and similarly the standard deviation of y is coming out to this divided by 31. Alright. So the standard deviation of y is coming out to 1348. So based on the multiplication of these two, covariance divided by the standard deviations of both these elements is giving me the correlation. So in this case it is coming out that the correlation is 0.61. So we know that the correlation lies between minus 1 to plus 1. So probably 0.61. Now the question comes out, is 0.61 a high correlation or a low correlation, right? So that is where I need to have some kind of a basis to test whether this correlation is high or low or no correlation. Is it negative? I mean, is it high or low or not even no, or even no correlation? Yeah, it lies between -1 to +1. Probably if it is 0.3, can I say is it it is existing or not existing? If it is 0.8, should I say it is high or low? Again, it should not be subjective there. It has to be, it's not relative. I have to test out whether it is high or whether it exists or does not exist. So just like any other hypothesis testing, we will do a hypothesis testing for the correlation also. So whatever number comes up, it could be 0.61 here, but when I calculate based on some other sample, I may get 0.3, I may get 0.2. 0.2, I need to know whether it is equal to 0, which means that 0.2 is it by fluke? Because some other sample I take, it may become 0 or it may become -0.1. So is it by fluke or is it consistently 0.2? Is it significant? So from that standpoint, just like the way we have done hypothesis testing for means and variances, we have to do a hypothesis testing for correlation also. So the test that is typically used for the correlation aspect, I'll come back to all these things. The test that is typically used for the correlation aspect is a t-test, where I use this formula r into square root of n minus 2, n is your sample size, r into square root of n minus 2 divided by square root of 1 minus r squared. That is the t statistic which we are using. So r is nothing but the correlation. So whatever, if it is 0.2 or whatever are the numbers. So in this case, let's say I am taking whatever we got through our sample calculation, 0.61. I put this into the formula. Look at it with n minus 2 degrees of freedom. Whether it is at 5% level of significance or 1% level of significance, I can define my business rule. Now putting the same, my t-test is nothing but r, which is 0.61, into square root of n minus 2, n is 32, so n minus 2 is 30, divided by square root of 1 minus r squared, 1 minus r squared. So this is telling me that the t value is 4.3, which is the t statistic for our computed value. For our case, the t statistic is 4.3. Now I have to say whether this, based on this t statistic, whether the correlation is significantly different from 0 or can I take it as 0. So the null hypothesis in this case is correlation equal to 0. Alternate is correlation not equal to 0, right? So from that standpoint, we are trying to find out for 30 degrees of freedom, what is the t value. Probably in your case, he will give it directly in the question itself, what could be the t value, in either in a table form or directly a value being specified, or because the sample size is more than 30, you can very well assume the numbers closer to normal distribution. 95%, so probably you can take it as 1.96 directly, right? So because the t value is lying outside the limits of -1.96 to +1.96, we will reject the null hypothesis. If the calculated value lies between -1.96 to +1.96, we are going with the null hypothesis. So which means correlation equal to 0. If it is lying outside the limit, we are rejecting the null hypothesis and simply going with correlation not equal to 0, which means it is significantly different from 0. So 0.61 means it is existing correlation. Whereas, let's say just for example, I get correlation as 0.2. My t value is only 1.11. Which we have to go with the null. We cannot reject the null. We are failing to reject the null hypothesis. So we are saying in that case, if the correlation is 0.2 also, according to me, it's nothing different from 0. Right? That 0.2 is a fluke. Just because of the sample which we have taken, that 0.2 is coming. It's nowhere different from 0. So even if it arrives to, let's say, 0.3, probably the same scenario. So 0.3 also is as good as 0 itself. So to say at what point it changes, or when should I take it as significant, it depends based on this test. If my sample size is very small, probably the t value, the correlation should be very high to say it is significant. If my sample size is very large, probably even with a smaller correlation value, I can say there is a significant correlation. So that's how we are looking at the correlation. So in this case, t value is 4.3. So we are directly saying there is a significant correlation existing. And in this, every correlation depend on the graph. It could be, if it is showing more on a 45-degree line, I am saying more or less it is correlated strongly. A minus 45-degree line more or less correlated negatively. But the real test is finding out the t-test. And in this data, if at all I came across that x and y are correlated very strongly. Now what is the intention of finding out that correlation? Using that y, I should be able to find out x, or using x, I should be able to find out y. So I have to make these two variables in such a way that one is a dependent variable on the other. Just by knowing one, I should be able to predict the other. That is where, based on the correlation, regression is coming into picture. The moment I am saying regression, the correlation coefficient plays a very significant role. The moment I find out R and R squared is nothing but it's nothing to do with the correlation there. R squared is the coefficient of determination. Now, what does it explain? Here, if I look at a smooth line here, if I look at a smooth line, there is a lot of variation of the points across the smooth line. So that variance, by what extent it is explained by my smooth line. So when I try to find out the variance of all these points, and I try to find out the variance of each point with respect to a line, by what extent is it different? One, I find out the variance of all these points, a simple variance, x minus x bar whole squared by n minus 1. Then I find out another variance looking at every point, the difference from the line. That difference, I find out the variance. We'll do that. Once we get a line, we'll try to do that. And that tells me if most of the difference, if most of the variance of my original data is present as a part of the regression line also, then it means that the explanatory power of that variable is much higher. So if I am using x to predict y, right, I am trying to find out the variance of y in isolation. I am trying to find out, using x, one formula to find out y. That formula of y, I will try to find out the variance. Like if I say y is equal to 2x plus 3, some formula came out to me. Now, based on the original data of y, I will try to find out the variance of y, which we have done in our case. Now, I will use the formula of 2x plus 3 and compute y. Now a new set of y's are coming. I'll try to find out the variance of those new set of y's. If I see that the variance of the new set of y's is more or less equal to the variance of the original y's, I say that there is a lot of explanatory power. There is a lot of deterministic power in my estimate. My estimate is a pretty strong estimate. The reason why I don't want to link it with correlation here is when we have multiple variables, here we are only talking about x and y. But the next thing which we would be looking at is x and y1, y2. In those cases, correlation is a word which I should not use. The reason being, correlation is always between two variables. But there we'll have three variables. So correlation will not be the word to be used. That's where we use it, though we compute it as R squared, but we still call it as explanatory power of the variable. Now, how strong is x in explaining y? Which is nothing but explaining in sense the variance of y, how much is it incorporated in x? The more it is incorporated, we say that the determination percentage is much higher. We'll try to compute the